Let's begin.
It's the 4th of June 1996, and the European Space Agency is launching its brand new Ariane 5 rocket for the first time. This is a big deal. The Ariane 5 is designed to carry large, expensive scientific and commercial payloads into space and heralds a brand new era for the ESA. A decade of design and testing and billions of euros have led up to this day. The Ariane 5 rocket carries no astronauts. The first payload is 4 very expensive scientific satellites to be delivered into orbit. Things start well. The rocket clears the tower and accelerates smoothly. And then the rocket abruptly changes direction, starts to break apart, and suddenly explodes. Less than a minute after launch, huge chunks and glowing fragments of Ariane Flight 501 rain down over the launch area. A shocking disaster for Ariane and the ESA. The cause? A simple, utterly avoidable coding bug. Okay, here's what happened. The Ariane 5 leaves the launch pad and accelerates smoothly into the sky, following its predetermined path towards space. Inside, the onboard guidance system is constantly tracking the rocket's trajectory and sending the data over to the main flight computer. To do so, the guidance system converts the velocity readings from 64-bit floating point to 16-bit integer. Okay, stop for a second, and let's think about what that actually means. Computers store numbers in a variety of ways. Consider 4-bit integers. 4 bits can represent anything from 0 to 15. But if you want to represent the number 16, well, there just aren't enough bits, are there? 16 is too big. You need more bits to store bigger integers. With 16 bits, you can store anything from 0 to 65,535. Or, if you throw in a sign, then 16-bit signed integers cover everything from minus 32,768 to positive 32,767. But anything bigger than that, and again, you've run out of bits. Floating point numbers are stored a bit differently. They're stored as a decimal, or significand, and an exponent. The details aren't really important here. All you need to know is that 64-bit floating point can store much larger numbers than can fit into a 16-bit integer. So converting between them can be tricky when the integer runs out of bits. So what does happen when you run out of bits? Well, if you're using 16-bit signed integers, the conversion will just wrap around to the beginning again. But whatever the details, you're definitely getting the wrong answer. This is known as an integer overflow. Right, so back to our rocket. The guidance system reads the horizontal velocity data of the rocket as 64-bit floating point and tries to convert that into a 16-bit integer to send over to the main flight computer. But at that moment, the velocity reading is actually larger than the largest possible 16-bit integer. The system tries to do the conversion and fails. Now, a clever system would have some procedure built in that says, hang on, we're piloting a rocket. I need to say something sensible to the main computer. It would have some overflow error handling code. But in this case, guidance system code isn't very clever. So it just sends an error message in place of the velocity data and promptly shuts down. Fortunately, there's a backup guidance system in case the primary module breaks down. Unfortunately, it's running the same code. So it does the same conversion, gets the same overflow, and crashes for the same reason. The main computer receives the error message, and because there's no handling code built in, the computer interprets the message as real navigational data and immediately freaks out. The velocity reading is off the charts, indicating that the rocket is dangerously, impossibly off course. So the flight computer does what it's designed to do. It fires up the boosters and drags the rocket around in an attempt to rescue itself from a non-existent disaster. This puts the fuselage under incredible aerodynamic strain, which starts tearing the rocket apart. Detecting that things are now really going badly, the computer calls it a day and triggers the built-in self-destruct mechanism. So, what was the ultimate cause of this incredibly expensive, very short, and ultimately catastrophic rocket flight? A simple line of code, converting a floating point to an integer that led to an overflow, passed without warning to the main computer, which was interpreted as real, if wildly inaccurate, data. The flight software had been used previously with no problems on many flights of the smaller Ariane 4 rockets. But the Ariane 5 was designed to fly faster than anyone planned for when the software was originally written. And the higher velocity led to the overflow error, a flaw that should have been found. It just never came up. Want to know the worst of it? That buggy bit of code wasn't even necessary during flight. It was part of the launch pad alignment process and shouldn't have been running after liftoff. But sometimes a small glitch somewhere causes a launch to be delayed by a few seconds. So to save having to reset the system, the original programmers decided to keep that bit of code running for 40 seconds after the scheduled liftoff time.
Okay. Let's see. All right, welcome everyone again to the second lecture of numerical methods. We're going to come back to the Ariane rocket and the type of error that occurred. It's a coding bug, but it's also what we call a round-off error. The next few lectures, we're going to be talking about errors exclusively. And so I thought this was a good motivating examples. As we move forward, you will see in my slides, you will see boxes colored differently. Blue colored boxes designate activities that you or your group are going to do, either individually or as a group. I'll let you know. Okay? You can be loud, you can discuss, you can talk, you have a few minutes to think about things. Okay? Coding activities are in this like greenish, bluish color here. We do those either together as a group or individually. A gray box designates a definition that you need to take into consideration as you study. This upper code snippet over there has this interesting, nice coding font to it. So those are code snippets. Boxes in yellow have some important statement to do, and boxes in this kind of slightly, it looks almost like the same yellow, but it's green, should be green. It's an example that we do together in class. I want you to start thinking about this first activity. If I give you this mathematical equation, what is the answer to x minus 1? The answer is exactly 1 for any value of x. All right. So now, I want you to take that same formula and run up your Python, your Jupyter notebook, do the same, this equation, x minus parentheses x minus 1 for the value of x 10 to the power 16. Here's a snippet of code. So you declare a variable x. Its value is 1e to the 16, so that's 10 to the power 16. You declare another variable, that's your result. This is where we're going to store x minus 1, and then we're going to print it. If you did this right, you're going to get your result to be 0. Okay? And if this doesn't shake your faith in computers, it should. Okay? It should shake your faith in computers. This error that you're seeing right here is what we call round-off error. And it's exactly the same what happened with the Ariane rocket. And we'll see a few other examples that were completely disastrous because of just crunching numbers on a computer. The culprit here is this parentheses here. Computers are gonna, like calculators, they're going to prioritize the calculation of what's in the parentheses first. So x minus 1, the computer is doing 10 to the power 16 minus 1. There is no room beyond 10 to the power 16 to include that single number 1. So from the computer's perspective, 10 to the power 16 minus 1 is equal 10 to the power 16. It's a very large number minus a very small number. Within a 32-bit computer, like all our computers, 64 bits, the number 1 is going to wash out. So it gives a priority to x minus 1, and that's 1e to the 16. And then you have 1e to the 16 here, you get result 0. When you take out the parentheses, it's going to go by order from left to right. It does x minus x, which is 0, and then plus 1 equal to 1 gives you the right answer. Okay? That's round-off error. Okay. All right, so we're going to start digging deeper into this. And the next few lectures are going to be on errors. But also, they're going to be an opportunity for us to start doing some coding together. okay, to ramp up all that knowledge that you need to know with NumPy arrays and matplotlib for what we're going to use later in the course. So there some aspects of these lectures are going to be slow, and some of them are going to be like just immediately, you know, a crash course in Python, okay? So try to keep up, review the lectures at home, the video, and then you'll be fine for the rest of the semester. I like to put learning objectives in every chapter or every unit that we're talking about. So at the end of these few lectures on error, you will be able to define and calculate what we call true error, relative true error, approximate error, and relative approximate error. You'll be able to identify when a true error, when an approximate error needs to be used, lists the common types of errors encountered in numerical analysis, essentially round-off, truncation, and their combination is called total numerical error. Identify which type of error is present in a given calculation. So if you're doing a Taylor series, for example, you just have this kind of round-off error that as you're improving on the digits. Or if you're using a truncated Taylor series, you have a truncation error that you're dealing with. Define the total numerical error. And finally, write Python code that computes the Taylor series to a desired tolerance to approximate functions. You'll also learn how to compute derivatives of functions and compute the errors associated with those. First, I will start by giving you just a general overview of the sources of errors. This is more qualitative in nature before we dig into defining errors. So in any engineering problem that requires modeling and math and stuff like that, there are a few types of errors that you deal with. Modeling errors, for example, these are errors related to the model that you are using. Suppose you're studying the terminal velocity of you like skydiving. Okay? You want to study your terminal velocity, you pick a parachute, etc. You want to run some calculations to see what your terminal velocity is going to look like. But then you choose the wrong drag model. Okay? So it's not going to, and then you go and jump and you're like, hey, wait, I'm flying much faster than I expected. Abort, right? So what happened there is you chose the wrong drag model. That's a modeling error. It's not a numerical error. Okay? There are programming errors. Yes?
Will this slideshow be on?
It's already on Canvas. Okay. So programming errors, these are mistakes in the code. Okay. So you make actually, instead of writing the true equation in the code, you put a typo there. You miss a number. It's not a numerical error. It's a coding error, almost like a human error. Okay. Finally, numerical errors, which is our main concern here. There are two general errors that we care about. Round-off errors, which is the example we just did when we subtracted a large number from a small number. This is the situation in all computers. When you try to represent a number that is larger than the computer can handle, it's going to round it. It's going to chop it off. Some people in computer science call that truncation error. We don't call that truncation error. We call that round-off error because we reserve the name truncation error to truncating a full mathematical formula. So you've done some math, and you've seen in a lot of cases you have these summations, these series that go from 1 to infinity. We can't compute anything to infinity, right? So we usually pick a few terms in that series, in that summation, 100 terms, 50 terms, 1,000 terms, but then neglect everything else. Whatever we neglect, we're going to call that truncation error. So that is still part of numerical analysis. Because in numerical analysis and numerical methods, you generally take a model is given to you, regardless of whether there are errors in the model or not. You don't care about that. Some modeling person gave you that model, those equations. Now you take those equations and you're going to put them on computers using numerical methods. That's where you decide, I'm going to truncate this a little bit here. We're going to use these 64-bit numbers, floating point here, or 128, etc. That becomes part of the numerical analysis. Okay. So the sources of errors and the types of errors, we're going to come back to this at the end of these lectures. But first, I'm going to discuss with you a few ways of measuring error and how we're going to measure errors in all our numerical endeavors as we go forward. So what's going to happen later, we're going to run a calculation. We're going to solve heat transfer in a plate, or like you're cooking something, and what is the rate of heat transfer? What is the temperature change in that eggplant that we are cooking? And we want to measure the error we committed in that calculation. Okay, so we want to define a few ways of measuring error. We will start with what we call the true error. True error, by definition, is the difference between a true value and an approximate value. Okay, before you start telling me where do we get the true value from, we're going to come back to that. It's kind of tautological here. Okay, and it's defined by this capital E, subscript T for true, and it's a true value minus approximate value. Whatever that means, you have a true value. Let's say you expect the concentration of PM 2.5 in this room to be 10 micrograms per liter, and then your sensor is measuring 9.8, then the error is 10 minus 9.8. Very simple, very obvious. Okay? So often we report this as the absolute value so that we don't get a signed number for the error. And I will tell you, calculate the absolute value of the true error, for example. Okay? Or calculate the true error. It really doesn't matter. It's just a question of convenience. Okay. So let's go ahead and do our first error calculation. And I'm going to give you your first numerical formula, which you've probably studied in your calculus or in high school. And that's the simple definition of the derivative, which is rise over run, right? So the derivative of a function is defined as the rise over an interval divided by that interval. Okay? So that's written as f prime of x for any function x, any continuous function x, is f of x plus h minus f of x over h. So you're evaluating the derivative at a point x, 0.5, let's say. Then you move a little bit on the x-axis by some distance h. Now, this distance is arbitrary, okay? But in the limit as h approaches 0, if you remember your calculus, then that definition becomes the exact derivative. Numerically, you can use that to your advantage. You can't put 0, but maybe you put 0.1 or 0.01, okay? So now we're going to try to assess the error committed. We're going to demonstrate that by using smaller values of h, you're going to get more accurate or less error in your calculation of the derivative. So h is some small value. Now you're going to go and compute this f prime for the function 2 exponential to the 0.5x. Find the true error in evaluating f prime of 3 using these two values of h, 0.5 and 0.05. So do this by hand. It's a calculation by hand. Use your calculator. So go ahead and compute f prime of 3 for this function, okay, using this formula with these two values of h. So your x value is 3, and your h values, you have two of them, 0.5 and 0.05. Okay? So go ahead. You can work as a group if you like, and I'll be walking around. Okay? Okay. Do you want to see what I got on my slides? Shall we? All right, here's my solution. And I will try this here to add some more slides about the solution process that we're going to go through, especially when we are converting theory into code. So first things first is I need to calculate the true value of f prime of 3 for this function 2e to the half x. Okay? The true derivative is given by f prime of x, which is u prime e to the u times 2. So you get 1 over 2 times 2, which is 1. You get e to the 0.5x as the derivative. And then finally, I get the true value of f prime of 3, or supposedly the true value. I'm going to show later that there's no true value ever. But the supposedly true value is 4.48169, however significant figures we can handle. OK, so now we have the true value. That's great. Remember, our objective was to calculate the error between the approximate derivatives, the true error for the approximate derivatives. So we need the true value. I got the true value. Check. Great. That's one of the unknowns that we were looking for. Okay. The next step is to calculate the numerical approximation. All right. So I'm going to put the true value on the side here. And I'm going to write that function again and the approximation, the rise over run approximation for the derivative. And the approximate value for h equals 0.5, I simply substitute So f prime approximate at 3 is equal to f. Remember, x is equal to 3. So f at 3 plus 0.5, which is f of x plus h, minus f of x, which is f of 3, over h, which is 0.5. And then substitute the value of the function f, which is 2e to the 0.5x, right? So you get 2e to the 0.5 times 3.5. That's 0.5. That's the factor outside. And this is x plus h. This is x over 0.5. You get some number for f prime of 3. And then we can evaluate the true error. I'm going to report the absolute value of that. And that's the true value minus the approximate value, 0.6. 60% error. Okay? Good job. All right. Now we do the same for the other value of h. Now what do we expect? We expect that for the smaller value of h, we're going to get a smaller error. That's right. Now that's called critical thinking, okay? As, in a way, right? It's such a banal example, but that's the process of critical thinking. Like, okay, what do I expect to see here? That's what makes you a little bit better or better than the AIs out there, okay? Is your ability to tell that something makes sense or not. I was working with ChatGPT this morning trying to create a probability density distribution. And I spent an hour with it trying to normalize that distribution because I know it needs to integrate to 1, and it could never figure that out. I'm like, you're dumb, I'm going to write it my own. So it took me 5 minutes to do my own distribution. Anyway, so that's what distinguishes you from the AI, is your ability to think critically about what to expect. Okay, so we expect a smaller error here. So let's run the numbers. Again, f prime approximate. This time h is 0.05. It's smaller, so you plug into the formula, plug and crunch. You get some value for f prime of 3. And then you compute the true error, and it's indeed 1 order of magnitude less. The previous error was 60%. Now it's 5.6%. Perfect, as expected. But that's just the true error. We computed an error now. All right. So let's see what we can do with this. Now I'm going to claim that this error does not tell us how bad the error is. So, okay, I told you, hey, I have a derivative approximation for the derivative, and the error is 0.5%. What does that mean? Is that a big error or small error? I don't know. Really, I don't know. So errors, because error measures should generally be provided relative to a reference value. So here's an example. Imagine you have a measuring device, and you're measuring this hypothetical platonic bridge. So from Plato, everything is ideal and perfect. You know exactly that that bridge is 1,000 feet long. Okay? And you have a measuring device, and that device always commits an error of 1 foot. So you go measure the bridge, it gives you 999 feet. So the error committed there is 1 foot. Now you take that device and you also measure a hypothetically perfect table that's 10 feet long. And the error there is also 1 foot. Which is a worse error? In the table, right? Why? Yeah. The 1 foot error with respect to the 10-foot table is huge compared to the 1 foot error with respect to the 1,000-foot bridge. It's insignificant for the 1,000-foot bridge. So intuitively, you understood that. You're like, right? Yeah, this doesn't make sense. So the error that I reported earlier did not take that into consideration, did not take that the value of the reference function that I'm computing this with respect to. Okay? It didn't take that into consideration. So we need to bring that into default for our errors to be a little bit meaningful. Okay, not just the nominal values. All right, so here's that example. So like your colleague said, there's a 10% error committed for the table. So we introduced the concept of the relative true error. So we're going to take that true error now, okay, and divide it by something. And that's going to be the true value. Okay, So the error in the bridge or the table, if we divide it by 1,000 or by 10 feet, then that gives us a scale that this is a 10% error. That's huge. That's a lot, okay? And it's a dimensionless quantity. It has no dimensions, right? So we define the relative true error by this epsilon term and subscript t for true, and that's the true error over the true value. Okay? So now we take that same definition of the true error, true value minus approximate value, and we divide by the true value. That normalizes everything. And then your error becomes presented in context, right? That applies to everything. A 10-degree error in temperature measurements for the sun is insignificant versus a 10-degree error measurement in a thermometer for your body temperature, right? You know, that could be the difference between you dying or like, but for the sun, it's like the surface sun is 10,000 kelvins. Well, it's 10 degrees or 100 degrees, doesn't matter, right? So relativeness is very important. Now, we typically report the relative true error as a percentage. You can report that as a percentage because it's a dimensionless quantity, right? And it's always normalized between 0 and 1 because you're dividing by definition by the true value, right? And so you multiply, well, sometimes you can get above 100 if you really mess up the approximate value. But in principle, like those should go up to 100%, and you report the error as a percentage, and then you move on with your life. All right? So now I'll throw this at you. Again, a 1-meter error is committed in measuring a 100-meter bridge and a 10-meter bridge suspension. So you have that bridge. Now we switch to SI units. Okay? And you commit the same error, 1-meter error, in measuring the 100-meter bridge and in measuring the 10-meter suspension. Which of those errors is worse? Go on. Talk about it. Either intuitively, give me the answer, or crunch some numbers. First, ask yourself what error is going to be important, a relative error or a true error or a non-relative error, right? Because the car is driving on the bridge and okay. So what do you think? The error committed in measuring the suspension is much worse than the error committed in measuring the bridge. Because a 1-meter error on a 10-meter suspension is 10% of those 10 meters, right? Versus a 1-meter error of a 100-meter bridge, which is 1%, right? So you need a relative error. So that helps you now identify not only in computing the value of the error, but also how bad the error is. Well, this is good or this is bad. You're an engineer. People are going to ask you like, okay, you did this report, you wrote this, and is this good or bad? Right? So you're going to be able to say that. Okay, so here's the calculation. So you get 1% when committing the error on the bridge, and 10% committing the error on the suspension. All right. So that ends it with true errors. Before I give you a break, I'm going to make a claim. Well, the last 10 minutes we spent don't make sense at all. Because I think true error doesn't make sense. Sorry. It's the process that matters in the education, right? So why do you think true error doesn't make sense? Okay. I saw another hand. Take a moment, think about it. Yes? Okay, can you elaborate on that?
True and error are antonyms, so they mean the opposite thing.
Okay. So here's my claim. If you knew the true value, right, why would you need an approximate value in the first place? You just use the true value, man, right? Who cares? Okay? Okay. So if we know the true value, why bother with computing an approximate value? Now, that's generally correct. However, imagine I bring you a device. So I've been tracking radon in my basement. I live in Sandy, close to the Granite area, and there's a lot of radon in that area. And I love to collect data. So I got this radon device, and I have over like 10,000 points of radon data. And I'm hoping to use it this year in this class to do some integration and kind of help me assess our health risk in our home. So I got this radon device, and I don't know, like, is it giving me good values? How do I know that? Right? How do I know that? So I need to calibrate it with respect to something that is truthful, okay, that has the truth in it, right? So if I could create a chamber and put a known concentration of radon in it, that's the true value, and put my radon device and take a measurement, then I can say with some confidence, like, well, this device has an error between, minus 2 to 2%, okay? Depending on temperature and pressure, etc. And then I can take it out of that design chamber and put it in different homes and hope that it's going to perform the same way. The same thing applies to numerical methods. You create a numerical method, you create an approximation to the derivative. How do you know it's a good approximation? You need to test it on problems where you know the true answer. That's your only hope. You know the true answer, you test your approximation on that true answer, and you assess the error, and then you're like, okay, this is reasonable. I'm now going to take it and apply it to cases where I do not know the true value, and hope that the error is still going to be bounded but by what we measured. So there is hope. You have a question? Yeah. So there is hope for true error. It plays a big role. In my field of research, I do computational fluid dynamics. We come up with these crazy, insane algorithms, hundreds of equations with a lot of kind of numerical math in them. And the only way we can assess that what we're doing is sane is we test on things that have exact solutions. Okay, we take the heat transfer equations, we take the fluid flow equations, we get reacting flow equations. For simple cases, we know the exact answer. We try our algorithm on it. If it gives us the same answer within an error, and we're like, okay, we are in the ballpark. Now we can take it and apply it to cases where we don't know the true value. Okay? That process is called verification and calibration, if you want. Okay? So then, okay, suppose we tested our numerical method on a system where we know the true value. How can we assess its performance on something where we don't know the true value? Why do we want to do that? Because we're like engineers and we're kind of annoying. We want to be able to get an error for everything. Well, there is hope in doing that. Okay, so let me guide you through an example. We'll do this, and then you can take a 5-minute break, okay? Now, suppose that you want to compute the exponential of 0.3, e to the power 0.3. That's some art generated by Dolly, so this morning. Anyway, so now you can grab your calculator to get an answer. Go ahead and grab your calculator and evaluate e to the power 0.3, okay? You get a number, e to the power 0.3, okay? Keep that number in front of you. Now, I'm going to claim that the answer that the calculator gave you is actually not even the true value. And in reality, in truth, we never know the true value of the exponential. Because the true value is a number with an infinite number of significant figures, right? Just like pi. We don't know how to evaluate the exponential. And in fact, what your calculator is doing, it is using some form of approximation to the polynomial, to that exponential. Some polynomial approximation like the Taylor series or some other polynomial that we're going to learn about. Why? Because calculators, in the end, all of the numerical math, all it can do is add and multiply, right? Or just add and subtract. So the exponential, it's not like x squared or x cubed. X squared, it's easy to evaluate. X times x, we know how to multiply. But e to the power 0.3, how do you do that? You get a table where, how was the table created? Okay? So your calculator is actually not giving you that true value. Okay? So that's kind of my claim. It would be surprising that this is. So your calculator is in fact using complex functions, expressing these complex functions as simple polynomials. So I'll show you, for example, this is what some of the calculators, there's a typo over there. This is what some of the calculators use to compute the exponential. It's a polynomial 1 plus x squared over 2 plus x cubed over 6 and so on. Those are easy to compute because x squared, division by 6, etc. Okay? So now, how can the calculator tell how many terms it needs to give a reasonable value for e to the power 3? In the previous example we did, you computed the true value of f prime of 3 on your calculator, right? We called that the true value. That's really not the true value. It's just an approximation with very, 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 very high accuracy. Okay? So where we left off was asking the question, how does the calculator know or tell how many terms it needs to provide a reasonable value for e to the 0.3 or cosine 7.8 or whatever, right? How does it know? There must be some internal mechanism in the calculator that is counting the number of terms and measuring some error, something to say like this is good enough. Because in fact, like if you look through some of the kind of communication with Texas Instruments or Casio, some of these big calculator brands, they preset a certain error tolerance. Say, you know, we're going to give answers within an error less than 0.1% or 0.01%. So the error is internally automatically adding more and more terms until it hits that error. So it is doing some measure of error. Okay? So let's try it out. Let's see what the calculator is doing. We're going to assume that the calculator is using this formula for the exponential. Other formulas are similar. They just kind of converge a little bit faster. So if you've done calculus, you might have heard of convergent series. The Taylor series is a convergent series. So the more terms you add, they're successively smaller, but they converge to the true value eventually. Okay? So what I'm going to do here, I'm going to evaluate e to the 0.3 and term by term. Okay? So first I'm going to start with one term and see the answer. Then I'm going to do 2 terms, and then 3 terms, and so on. And know that I don't know the true value because we're being the actual calculator right now. Okay? So we don't know when to stop. So let's see. With one term, the result is 1 because that's the first term in that polynomial, in that series up above, right? With 2 terms, you have 1 plus x, that's 1 plus 0.3, that's 1.3. Okay? With 3 terms, you have 1 plus x, which is 1.3, plus 1 over 2x squared, which is 1 over 2 times 0.3 squared. So now you see how you're starting to build more and more significant figures. Okay? Now with 4 terms, you get 1.3495, and so on and so forth. Now I went ahead and wrote the code for whatever number of terms up to 20 terms, and this is what I got. With 4 terms, that's where we left off with the previous slide, we got 1.3495, then 5 terms, 1.3498, 49858, 588, 588, and so on, and then something happens. What happens? Something happens after, what, 10 terms? What happens? What do you see in the result? It looks the same, right? So it's not changing anymore. So the calculator cannot do any better. Or the formula is just not going to do any better. It's meaningless. We can carry more digits, but I'm here assuming that you're interested in like maybe 10 significant figures, okay? You can carry more digits, but the change is happening way behind those digits, which for practical purposes doesn't matter, okay? But something happened here in that after 10 terms, 11 terms, well, term 12, then there's no more change. So can you use this fact that there's no more change after a certain number of terms to tell the calculator to have an internal mechanism to say, stop here. Because clearly, the calculator is not going to spend an hour computing 2,000 terms or 10,000 terms. That's more than enough, or maybe not. We don't know, right? So maybe it can do it in 10 terms or 5 terms. So can you use this fact that after some point, the calculator cannot do any better with the result, and it should stop there? Can you use this fact to come up with an error measure, with something that looks like an error? And it's a difference between two things. Okay, what if we track the result between two approximations, between 5 terms and 6 terms, and then between 7 terms and 6 terms? Take the difference. Can we say something there? We can say, well, if that difference between successive terms doesn't change anymore, or the change is only 1%, or 0.5%, or 10%, then stop there. Right? Would that work? Then that would say, well, between 8 and 7 terms, the change is about, I don't know, maybe 1%. And our tolerance in our Texas Instruments calculator, I'm not advertising for Texas Instruments. I'm not affiliated with any of those companies. So, the calculator is going to say, I'm going to stop there. Because all my tolerances in there are 1%. So we're going to stop there. I'm going to keep, because I cannot do any better. The calculator cannot do any better. But the trick is to trust that the Taylor series or that polynomial actually always converges to the true result. Okay? So that's the power we have from math, from the theory, is that series, the more terms you add, the better you're going to get. So any approximation with more terms is better than with less terms. So we know that with 10 terms, we're better than 8 terms. So if we take the difference between the two, that's a very reasonable measure of error in practice when we don't know the true value, because it's the best we can do. Okay? And that's exactly what we're going to do next. I added one column here to take the difference between successive terms. So you see, with the first term, there's no error because there's no previous term. But then with 2 terms, you take 1.3 minus 1 gives you 0.3. Then 3 terms minus 2 terms, you get 0.045. And quickly, the error, that difference goes to 0. Okay? And then we can tell we're going to stop there when the difference is less than 1%, 10%, 0%, whatever. Okay? So we call that approximate error. Kind of obvious. We don't know the true value. We're doing an approximation, so we're going to approximate the error. This is approximately what is happening in this system, in this numerical method. Okay? And the approximate error now is defined as the difference between a current approximation and a previous approximation. The current approximation is the one where you have more terms, and the previous approximation is the one where you have less terms. Okay? So we write that as E subscript A. Okay? There is an underlying assumption here that current approximation is a better accuracy approximation than the previous approximation. Why? Because we know that from theory. That's been proven by the mathematicians. That Taylor series converges. That means more terms is better than less terms. So we trust that result. So the current approximation that has more terms is better than the previous approximation with less terms. There's a stronger statement of that says the approximate error is defined as the difference between a more accurate approximation and a less accurate approximation. Again, how do we know one approximation is more accurate than the other without knowing the true value? Well, the math tells us that. The derivation of the mathematics tells us that. We're going to hit a point a couple of months into the semester where we see that. Okay? It all goes back to what the truncation error is. Anyway, but the math can tell us that. The math can tell us this is a method of what we call order 4, and this is a method of order 2. So this method is more accurate than the other method. We take the difference that gives us an idea of the error committed in those approximations. Okay? So you can use whichever one you want, but also we need to define a scale for those errors. So just like the true error, we defined a relative true error. For the approximate error, we are going to define a relative approximate error because we need a sense of how big that error in the approximation is. So we simply divide by the better approximation. So just like with the previous definition where we divided by the true value, here we're going to divide by the more accurate approximation. So I really like this definition, more accurate approximation minus less accurate one over the more accurate one. You put absolute values on those, you multiply by 100%, and that gives you a really nice percentage error to evaluate your numerical methods when you do not know the true value. Okay? When you do not know the true value. Almost exclusively from here onwards, we are going to be using one of these errors to assess our numerical algorithms and how well they're doing. Okay? So, let's go ahead and do an exercise together. Again, I'm going to go back to that derivative. And now, you call that rise over run. I'm going to introduce the terminology for that formula, and that formula is called the forward Euler formula. Has anyone heard of that? Yeah, forward Euler formula. Okay, if you haven't, first time you hear about it, it's the forward Euler formula because it's taking, why it's forward? Because it's taking f at x plus h minus f at x, okay, over h. We're going to come back to that once we hit ordinary differential equations later on. So here's the exercise that we're going to do together. We're given this forward Euler formula, f of x plus h minus f of x over h, and h is some small value. And again, from the math theory, we know that derivatives with smaller values of h are more accurate than derivatives with larger values of h. So that anchors the meaning of those terms in the calculation of the approximate error. So the question is, for that same function we dealt with, 2e to the half x, find the relative approximate error in evaluating f prime of 3 using these values of h, 0.5, 0.25, 0.125, and 0.0625. So what I'm doing here, I'm starting with value for h, and then I'm cutting it in half, and then I'm cutting it in half, cutting it in half, and I want to see what happens to the error, to the relative approximate error. Okay. So here's my solution plan. We are given a formula that approximates the derivative of any function, and the formula depends on some parameter h, and we know for a fact that the smaller the h value, the more accurate the answer. So that should give us that critical thinking step that, okay, I'm doing these numbers. I should expect that the error with smaller values of h is going to be smaller than the error with higher values of h. So that's your sanity check, okay? And then we are asked to compute the derivative of this 2e to the half x for these different values of h, 0.5, 0.25, and so on. And then find the relative approximate error. So how do we find the relative approximate error? We need to evaluate the approximate derivative for each one of those values of h and take the difference between the better approximation minus the worse approximation and divide by the better approximation. Okay? And I'm going to do them successively. You can take the value between this one and treat this as the better approximation. That's fine. Okay? But what I'm going to do, I'm going to take the value between 0.25 and 0.5, and then 0.125 and 0.25, and so on and so forth. Okay? You're not wrong if you do pick any one better approximation minus the worst approximation. Okay? You're not wrong in doing that. But there's a reason I clustered them together, because there's something that I'm going to allude to eventually once we're done with this exercise. And for each approximation, we compute the approximate error based on the difference between the better approximation and the one just before it. Okay? So I love tables. So here's a table with hidden lines about what we're doing here. So this is the function 2e to the half x. The approximate f prime is fx plus h minus f of x over h. And then evaluate it at x equal 3. For the first value of h, I cannot define an approximate error because I don't have a better approximation. The error is essentially undefined, okay, NA, or not available. For h equals 0.25, you plug in the numbers, you get f prime approximate at 3, 4.77, then you take the difference. 4.77 minus 5.09 over 4.77, and you get 6.66%. Okay? All right. And that number is complete coincidence, by the way. Okay, so 0.125, at age 125, you get 4.62, and then bam, you see from 6.66 to 3.22. Okay? And then you continue at x at h equal 0.0625, 4.55, and you do the error, 4.55 minus 4.62 or 4.55, and you get 1.59%. Okay, can you identify a pattern here in the error? Okay, so h, for each value of h, I'm cutting it by half. From 0.5 to 0.25 to 0.125 to 0.0625, right? What happens to the error? From 6 to 3 to 1.5. I'm cutting h by half, and the error is also being cut by half. Okay? So later we're going to learn that this is a first order method. We're going to learn that once we study ordinary differential equations. Okay? But there is a pattern here. As we cut h in half, so if I ask you in the homework, what happens when you observe the, I'm going to give you a different formula. I'm going to give you a different formula for the derivative. That is second order or a fourth order method. What happens as you cut h in half? The error might be cut by a factor of 4 or a factor of 8. So those are even better and better methods. For this method, it just so happens that you cut h in half, you also cut the error in half. Okay? All right, so now we have, 15 minutes to do some Python activity. All right, let's do this in Python now. Okay? Get your Jupyter notebooks, your PyCharm, your Spider, okay? And we're going to solve this problem together now. Again, for that same function, 2e to the half x, the objective is to create a Python routine that computes the relative approximate error when approximating the derivative using the forward order formula at x equals 3. But now I have a wider range of values for h, 8, 4, 2, 1.5, all the way to 0.0625. And I want to report the percent relative approximate error. Okay? Get your Python up and ready. And I'm going to do the same over here, and I will guide you through it. Okay? Let's see. So on my end, I am going to create a new Jupyter notebook. So I apologize. I'm going to have to turn to the side a little bit. This cable is not long enough. Let's see. This cable is long enough. Allow me. Oops. Come on. Okay. Okay. So I'm going to move the window. Okay. So we're going to work on this together, and along the way, we're going to pick up some Python tricks. So for those in the back, can you see? Okay. Oh, well, you cannot see now. Okay. So the first cell, I'm going to convert it into a text cell. You might know this. You might have gone through some of the tutorials and whatnot, but let's just do it together. Right? So if you go here and select this cell, you can put code or text in it. By default, a cell is a code cell. Okay? So whatever you type in it is going to assume it's code. So if I go and write, my name is Professor Tony, it's going to tell me it's an invalid syntax. I'm like, what are you talking about? My name is Tony, right? Well, because this is a coding cell, and Python doesn't recognize this yet, that my name is Tony. So what I'm going to do is I'm going to convert this cell into a text cell. And if I click on cell and go to cell type, and I'm going to select Markdown. Markdown is the text equivalent, is the text syntax that you use in Jupyter notebooks. Okay? Is this new to any of you? If you know this, we can hit the ground running. Is this new to any of you? It's new? Okay. Okay, so we'll go through it. Okay, so you can go click Markdown, and now it's a text cell. So if I execute it, it turns into text. Now, how did I execute it? You can press Shift-Enter. So you are inside the cell. You can press Shift-Enter, and you have the name there. And so I'm going to change this now, and I'm going to say in class coding activity for approximate error. Okay? But I kind of want it to be a heading, so it's like a big thing. Okay? So I can double-click on it and go to the beginning and put the sharp symbol. Bam! Look at that. That's cool. Okay? So now I need a cell. One more. I need to convert this cell into text. I can go back here, click cell and cell type, and go Markdown. Oh, but look at here. There's like these little symbols here, M and Y. These are shortcuts to convert a cell either to a text cell or a code cell. So if I go back, just get out of here, okay, and just click on this one. If I type M, it converts it into a text cell. If I type Y, it converts it into a Python cell, a coding cell. Full shortcut. Okay, so now I want to convert it into a text cell so I can write some description in it. So I'm going to type M and then press Enter. It puts the cursor inside it. In this notebook, we will compute the approximate error for the forward Euler method, etc. I'm being brief here, so in your homework assignments, do more. Okay, but in the interest of time here, I'm going to be all brief, and I'm going to take shortcuts, okay? Right, etc., etc. Okay? And now you can also put math in it. So I'm going to go back to this cell, okay? And I'm going to put the equation for the forward Euler method. Okay. Now, Markdown uses LaTeX. Anyone familiar with LaTeX? Okay. That's fine. You know, I learned LaTeX by example. We have a lot of LaTeX resources in the files directory under homework. There's a folder called LaTeX and Markdown help, cheat codes for how to write equations in LaTeX. Once you get through a few examples, you're up and running, and it's non-issue at all. So check how beautiful this will be. So I'm going to write an equation, and this is the syntax for equation. Don't ask me why. I did not invent this, but that's how it's invented. Okay, f prime of x equal, or okay, f prime if x is equal. I'm going to do a fraction. So that's backslash frac, numerator, denominator. And that's f of x plus h minus f of x over h. Now, if I execute this cell by pressing Shift-Enter, look how beautiful this is. This is a high-quality vector graphic equation that you put, not some ugly text-written thing that you would do in Word or using whatever word math it has. This is true high-quality math, okay, that you can typeset and have a high-quality product. You appreciate a high-quality product, right? And others appreciate a high-quality product from you as well, okay? So use this. It will make everything stand out. Okay. Let's get coding. I always like to import, we call them the boilerplate, that there are a few libraries that we're going to import all the time in this class. The first one and most fundamental is going to be the NumPy library, okay? And it's just a library provided by Python, any Python distribution. The way to call a library is just type import NumPy. How do I know NumPy is important? Because I learned it, right? Now you know it's important, okay? Now, if I import NumPy, it's going to be annoying every time I want to call something from NumPy to type NumPy dot, et cetera, et cetera. So I'm going to give it a nickname. I'm going to call that nickname NP. So import NumPy as NP. From now on, everywhere I type NP, I can access the entire library of NumPy. NumPy has arrays, has math equations, formulas in it, has functions, has all sorts of crazy stuff in it. Every time I type on NP, I can access something from that library. How do you access something from that library? You use the dot designator. So if I do NP dot, then I can access all sorts of things from NumPy. So check this out. Okay, so NumPy dot, let's say exponential. So it's going to give me the exponential function. And if I type NumPy e to the 0.3, it gives me a value, 1.34 or whatever. Okay, so that's great. That's our NumPy function that we're going to use. All right. So the first approach, I have 5 minutes. Maybe we'll do this, and then we come back on Tuesday and continue on this example. The first approach is the brute force approach, and we're going to be using Python just as a silly calculator. Okay? You're allowed to do that. Nobody is going to duck points for that. We're going to tell you there are better ways of doing it because this is a full-fledged programming language. But the first example we're going to demonstrate is using Python as a just simple, very fancy calculator. Okay? So what that means is I'm going to take this problem statement. Let me get the slides over to the other side. Okay. Okay. So these are the source for my slides. So what I'm going to do here, I'm going to evaluate this f prime for each one of those values. I'm going to store the derivative, and then I'm going to compute the error and do it one by one. I'm not going to do for loops. I'm not going to do any of that. Okay, we're just going to use it as a glorified calculator, just to tell you that, yeah, you can do it that way. It's not going to be productive, and we're going to show you a better way of doing it. But that's the first step. Again, I use the inductive method in my approach. So if you know this, you can be yawning, do it your own way. That's fine. We're eventually all going to catch up together. All right? So here's what I will do. First, I want to declare my x value, which is x equal 0.3. Okay? So now I put the value of 0.3 in x. So now everywhere I call x, it's going to contain the value of 0.3. All right? So now let's start doing, start computing the approximations. Okay. So for the h value of 8, remember that was the first h value, my advice to you is always put a decimal point to enforce the fact to Python, to tell it that this is a floating point number, not an integer, so that Python doesn't try to outsmart you and assume that you're doing integer arithmetic and you end up crashing Ariane 7 or something, okay? So when you put 8.0, you tell Python this number is a floating point number. Don't treat it as an integer, okay? Make that a habit. Unless you are doing integer operations, you put a decimal point. It's in your best interest, okay? Now I'm going to compute the derivative, and I'm going to call it df8, let's say, because that's the derivative at h equal 8. So df means derivative df by dx, right? Or f prime. And that's going to be 2.0 times numpy.exponential of x plus h, okay, minus 2.0 times np.exponential. Oh, I forgot the 0.5. Okay, there's another 0.5 here, times x plus h, okay? And there's another 0.5 times x, okay, divided by h. Now notice, as I'm moving my cursor, look how it highlights the green, the parentheses. So it matches the parentheses. See, I'm by this parentheses. It's going to match it with this one. Then I go this one, match it with this one, and so on. Okay? And notice that I have to do the multiplication sign. If I don't do the multiplication sign, like here, between 0.5 and x plus h, it's going to throw an error. It's going to barf. Why? Because in programming languages, parentheses designate a function call. So 0.5 and followed by parentheses, it's going to think that 0.5 is a function. And you're calling something on that function, but 0.5 is not a function, it's going to freak out. abort, abort, okay? So put your, don't forget your multiplication, okay? Okay, great. df8 is, it executed, okay? So now, what is it doing? Did it compute a value? Yeah, it did. How do you know that? You print it. My best debugging tool in the world is to print things out. Okay, print df8. Oh, it produced a value. Great. Okay. There's a saying that I've said since 2017. Okay, that everybody knows, and I see Ariana and Ainsley are laughing in the back. And it says, when in doubt, print it out. When in doubt, print it out. So that's what we're going to do as we move on.